Thank you. First I'd like to thank the organizers for inviting me and for the opportunity to speak here. It's really a great pleasure. And then, before I start my talk proper, I would like to draw your attention to the fact that in 2019, the version of this conference will be held at Uppsala, and I refer to this homepage that exists. There is so far very little information on that, but anyway, if you keep checking, then there will be. Okay, so I hope that many of you can come. Okay, so the talk will be various bits and pieces. So first, I will, in fairly brief, talk about the background, which is well known to some of you and maybe others not, and so on. But anyway, it will be short. And then I want to talk about augmentation varieties and convergent disk potentials. So this is about joint work with Aganagi, Wafa, and Lenny Ng from a couple of years back. And the main part then of the talk is about generalization of that work to higher genus, and that involves defining what's called Lechandrian symplectic field theory, and also there will be a kind of a genus by genus construction of all closed Gromov-Witten invariants. So I want to explain that as well. We'll see how I'm doing on time. Okay, so let me try to give the setup. So we start with a k-component link in the three-sphere, and associated to that there is a Lagrangian in the cotangent bundle of the three-sphere, so it's co-normal. So all the co-vectors that along the knot that or link that kills the tangent vector. And so topologically, this is just, each component is just an S1 times R2. There is also, so the main kind of idea of all this not-contact homology from point of view of relating it to Gromov-Witten theory is that you try to compute things from infinity, and the infinity that we will be using is the infinity of T star S3. So that's a 5-dimensional contact manifold, which is the unit or sphere-sized cotangent bundle, with a contact form, which is the restriction of the action form. And inside there, the trace of the Lagrangian conormal is the Lechandrian conormal. It has the topology of a torus for each component of the link. So the thing that we are going to relate holomorphic curve counts, etc., to is Chern-Simons theory. And just to set the definition, I want to introduce notation for the colored HOMFLY polynomial, where the jth component of the link is colored by the mjth symmetric representation. And there is a expression of that in terms of Chern-Simons theory as up on the board, and we are going to collect all these colored HOMFLY polynomials into something that I call the wave function. So it's just exactly the coefficients are these colored HOMFLY for various colors, and we keep track of which the colors are by exponentials. Okay, and the variables are somehow the usual ones. So the geometry that we will do will take place in the resolved conifold, which is the total space of local CP1. And both the resolved conifold and T star S3 can be viewed as resolutions of the same cone in C4. And in particular, topologically, if you remove the zero section from both of them, they're just S1 times S2 times R. And symplectically, they're not quite the same. So if you remove the zero section from T star S3, then you have this S2 cycle in the fibers. And if you view that as living in the resolved conifold, then this sphere has symplectic area, some finite symplectic area. But when you go very, very far out in this conifold, resolved conifold, or in T star S3, then this symplectic area is somehow very small compared to the action form in T star S3. So from point of view of things like holomorphic curves, actually it's somehow this X is sufficiently asymptotic to T star S3 so that we can just deal with the infinity as if it was the infinity of T star S3. There is a kind of little bit more ingredients before we can start working. So that's the construction which allows us to move the conormal of our link from T star S3 into X. Now, the conormal, of course, intersects the S3 along the link itself. And so we'd like to shift it off, and we can do that keeping kind of Lagrangian condition, but violating exactness. So Lagrangians are called exact if this PDQ restricted to the Lagrangian is d of some function. So the form is closed, that's the Lagrangian condition, but if it's also exact, then it's exact. But here we violate this thing, and what we do is we just shift it up in the direction of the form dual to its tangent vector. So in a small neighborhood of the knot, the manifold looks like S1 times D2. And in there we have the standard S1 form d theta, and we shift the conormal along this direction, and then it's off the zero section. We can view it now as Lagrangian in X. And in particular, just as before when we had no knot, this Lagrangian with respect to holomorphic curves and so on works exactly like the Legendrian times an interval in T star S3 near infinity. Okay, so now we are going to relate the introduced HOMFLY invariant and open topological strings, or if you want Gromov-Witten theory. So the first step is Witten's result relating UN Chern-Simons theory and a model topological string in the cotangent bundle of S3 where you put n branes along the zero section. So, and the next step is work by Kupakumar-Waffa and Ogura-Waffa, which transforms this open string theory to closed string theory in the resolved conifold. So this is the large N transition, and I will discuss kind of details of this a little bit more later. So somehow, as you know, the string coupling constant times n is supposed to be kept constant and become the area of the CP1 on the other side. And if we combine these two results, then we get an interpretation of our HOMFLY wave function as the Gromov-Witten partition function, which counts holomorphic curves in the resolved conifold with boundary on the Lagrangian conormal, which we now view as sitting inside the conifold. And here is the relation between the variables that I was talking about. So first, the string coupling constant is related to the level of the Chern-Simons theory, and then the area of the central P1 in the resolved conifold is given by n times GS. Okay, but what we should just remember from this is that, and we will mainly deal at first with the right-hand side of this equation. So we will have this wave function which counts all holomorphic curves with boundary on LK inside the resolved conifold. Now there is a when we do this transition, we have the LK sitting inside, and then in this Witten spirit, we're looking at the holomorphic curves from LK stretching down to the zero section, and they become the closed curves on the other side. And in some sense, the remaining curves are those which never leave the constant curves along LK, and we would like to quantize that theory. And arguing in the same spirit, you can see that the path integral is just a path integral of ordinary quantum mechanics in the periods. So what we should do is we should just upgrade the periods or the homology generators, X, which I call the notation for the longitude in this conormal torus, and P, which is the meridian, which is the one that is filled by the conormal in this way. So P is replaced by GS ddx. So I will in fact give kind of enumerative interpretation of this later, so let me leave it at that now. Now, once we see this, then we can expand the wave function in sort of standard manner, and this gives us that the first term is, well, it's exponentiated, but then it's just given by integral p dx. On the other hand, if we think of this exponent in the wave function as given by curve counts, then the corresponding genus parameter at this point is the value 1, so that means that we're counting holomorphic disks. So what this equation tells us is that there is a relation between the meridian variable P and the Gromov-Witten disk potential. And when we think of the full, so I should go back, when we think of the full quantum story, so there is some kind of Schrodinger equation for this psi, which is the recursion relation for the color HOMFLY. Then this kind of Lagrangian variety should be a parameterization of the corresponding algebraic variety when you let the variables commute. So we find that this equation should be actually given by some algebraic Lagrangian variety in terms of e to the x and e to the p. And then there is also the q parameter, but I view it just as parameter. So as it turns out, and that's the starting point for all this story, is that this variety is in all examples equal to the augmentation variety of not contact homology. And this relation actually gives us a way of counting holomorphic disks. So this is a very non-trivial problem to count these disks inside. It's hard to find them in general, for general knots. But we can then count them from infinity in a much easier way. So that's the main starting point for all this story. And I will try to explain what this augmentation variety is next. So for that, we need to understand what is not contact homology, and not contact homology is a Floer theory, which is known either as Legendrian contact homology or maybe just Chicano-Villiers-Berg algebras, applied to the Legendrian conormal of the knot or link. And to give a very brief description of what this theory is, it wants to do the Morse theory for the action functional, the kind of contact action functional, which in the contact manifold, which is here the unit cotangent bundle, looks at paths beginning and ending on the Legendrian, and then integrates the action form along these paths. And so basically what you should have in mind is we want to do the Morse theory of this function on that infinite dimensional space. So the first point is to find the critical points. And the critical points are what's called Rabe chords. So Rabe chords is just what you get if you vary these, and then you find that in order for a path to be stationary, the tangent vector should be in the kernel of the derivative of this form. And then the second condition is just the normalization condition. So we normalize the vector field to be, the form to be 1 on the vector, normalize the vector field so that the form evaluated on is 1. Okay, so now the knot contact homology algebra is not quite as in Floer theory, the chain complex generated by critical points. It needs to be a little bit more complicated, and I'll explain why in a second. So rather than that, we need to use as chain complex an algebra generated by these Rabe chords. So we cannot somehow take single Rabe chords, but we need to take all possible words of Rabe chords. And the differential will count holomorphic disks, and for that matter, we will have coefficients in the second relative homology of the Legendre inside the contact manifold. So in this case, there are this second relative homology is just 2 variables for each torus component, which is their H1s. And then there is this Q variable, which corresponds to the closed S2. Okay, so there is also a grading on this algebra. And in this case, it's not so hard to understand because this PDQ contact form has Rabe chords which are just lifts of the geodesic flow. So the Rabe chords of the conormal are exactly geodesics which are perpendicular, oriented geodesics which are perpendicular to the knot at both endpoints. And moreover, this grading in this case is also easy to understand. It's just exactly the Morse grading of the geodesic chord. So if we think of the knot as lying, it's really in S3, but think of it in R3, then this grading has only values 0, 1, and 2. So that's a very good thing for calculations. So and the main point with this algebra is, of course, the differential, and I will explain it next. So it's an algebra differential, so that means that you just need to define it on generators and then extend it by Leibniz rule. And okay, so the resulting algebra is invariant under deformations like isotopies and choice of certain data. But let's look at what the differential looks like. So this is a picture of the differential. So the input of the differential is 1 Rabe chord. And the output should be a word of Rabe chords. And the differential counts holomorphic curves with a specific almost complex structure. So our holomorphic curves, so here Y is shorthand for this sphericized cotangent bundle. So we take our contact manifold and multiply it by R. So this is called, then if you equip it with the certain symplectic form, the symplectization of our contact manifold. In this case, it just looks like T star S3 at infinity. And we take on there an R invariant almost complex structure. So that means that everything is invariant under the R translation. And moreover, the almost complex structure pairs the real direction with the Rabe direction inside the contact manifold. So that means that if you have a Rabe chord and you multiply it by R, then you have a holomorphic strip. And our holomorphic curves, they are required to be asymptotic at positive infinity to this Rabe chord strip of A and at negative infinity to the Rabe chord strips of B1 up to BK, and the boundary is sitting on R times lambda K. This is an elliptic system, etc. So there it has a dimension, and we are looking for those which have dimension 1. So only this stupid R translation is there. So the rest is somehow rigid. Now, when we count these things, we could just, as the first attempt would be to just count them, but we count them in a little bit more refined way. Namely, we look at this curve, which is a 2-dimensional object with boundary in lambda K times R, and we take its relative homology class. To be completely honest, you need to cap it off a little bit with some disks, but let me not discuss this. But this is what we're doing. So we kind of keep track of the relative homology class of the curves, and then we count them like that. So this is the differential. So now one might ask, why is this a differential? So the main point is that when you take d twice, it should square to 0. And the reason for that is a compactness theorem. This is somehow called symplectic field theory compactness. So it's like Gromov compactness, but it stretches in one more direction. So basically what you have to do is you look at the two-dimensional such moduli space. So there is a stupid one dimension, which we can quotient out by. So then we're left with a one dimension. And the boundary of this space consists exactly of two-level holomorphic curves. And it's an oriented one manifold, so its ends cancel. Now these two-level holomorphic curves are exactly what appears when you take d and then take d again. So d squared is 0. And here you see also the reason why we have an algebra and not just a chain complex. So if you imagine that you try to define a chain complex, then you take two holomorphic strips of dimension 1 and dimension 1 and you glue them. And this goes into two-dimensional moduli space, but now it could be that this curve splits into the configuration on the right, which is certainly not a composition of two strips. So therefore d squared is not equal 0. And this algebra, then when we take one positive and several negative punctures, is somehow the minimal resolution of this problem. So that's the minimal thing we can do. And that's why we have to define an algebra. Okay. Note also, I go back one. So note also that this algebra, in fact, is generally not commutative because we have an order of the punctures on the disk. So it's actually a non-commutative algebra. Okay. So this is the definition of some kind of Floer theory. We get an algebra, its deformation class is invariant of the Legendrian isotopy class, therefore also invariant of the knot. So that's great, but the question is, can we actually compute this knot invariant, or in what way? It turns out that in this case you can do it, and it maybe takes a lot of work, and it's usually difficult to compute Floer homology, but here you can do it, and the result is that if you have a braid, present your knot as a braid, then you can present the algebra with basically n squared and 2n squared in 1 degree generators, and the differential is given by an explicit expression in terms of the braid. So that's good. So we kind of have the algebra, the differential. That doesn't mean that this is a very useful invariant in itself, because it's somehow not so easy to, distinguish such algebras given in a complex and complicated way. But let's nevertheless see some examples of what happens. So if you take the unknot, then the algebra has actually two generators. So if you think about it, the unknot living in a plane, we're supposed to find binormal chords. So there's a whole S1 family of those, but that's a kind of bot situation, so you can Morsify it, and you would have two Rabe chords called C and E. And D of E is 0, and D of C is the following expression that you see on the board is 1 minus e to the x minus e to the p plus q e to the x e to the p. And that derives from 4 holomorphic disks with boundary on this conormal. So intuitively you can think of them as this chord shrinking away in two ways to the 0 chord. And in fact, when you look closely at this shrinking away, there are 2 ways of closing up the corresponding disk, and they live in 4 different homology classes on the torus, and one of them has a kind of S2 in it. Just to for future reference and to see what happens, so that this is a little bit too trivial in some sense to see what it looks in general like. So if you take the trefoil knot, then the corresponding algebra has a few more generators, and the most important part of the differential is the one that maps from degree 1 to degree 0, and it looks as follows. So you see that for the trefoil, there are somehow some quadratic polynomials in this A12, A21, but it's even a cubic term, but not more. If you have more complicated knot, it would be much worse. Okay. Now, the last ingredient in this story is this augmentation variety, and how to understand, we need definition. So we consider these algebras. Remember, they were algebras over the group ring. So there was kind of one e to the x, one e to the p for each component. And we consider it as a family of algebras over c star to the 2k. So where the values in the c star to the 2k are the e to the x, e to the p. And then an augmentation is just a representation of this algebra into the complex numbers, where we equip the complex numbers with a trivial differential. So that means representation, or maybe chain map better. So since we have the trivial differential on the complex numbers, that means we just have to require that this epsilon composed with the differential is 0. And now the augmentation variety is the variety where we have an augmentation. If we don't have an augmentation outside this locus, somehow the homology is more or less trivial. So this is the interesting locus, and we take its algebraic closure. So this is the augmentation variety that is in fact related to this algebraic variety coming from HOMFLY polynomial. Okay. So let's see what we get. So remember, for the unknot, we had a differential at just 1 degree, 1 generator. Its differential was this. And so if you want epsilon composed with differential to be 0, you just have to require that this expression is 0. So the augmentation variety of the unknot is simply the 0 locus of this one polynomial. If we move on to the trefoil, the augmentation polynomial becomes a little bit more complicated. So here it is. But let's not stare too long at it, but let's go back and see what kind of task we're facing if we want to compute it. So here, what we are supposed to do, we are supposed to assign, think of this e to the x, e to the p, and q as numerical values. Now we're supposed to assign numerical values to the a12, a21 in such a way that all these equations are 0. So in other words, we are looking at the problem of finding common roots for all these equations, and that's a problem that's solved by elimination theory, right? So in particular, we find that the solution is some, algebraic set, and that is this algebraic variety Vk, and you can in some sense compute it, as you see from. I mean, it's not an easy task, but you can somehow do this elimination theory if you're given some time. Okay. So the next task is to try to relate the two things. So we have this derivative of the Grom-Witten potential, and we have the augmentation variety, and they should be somehow related. And the starting point for this relation is the fact that if you have some exact Lagrangian filling, it doesn't matter so much what it is, but in fact I maybe even gave the definition, but I want a Lagrangian that looks like my Lagrangian LK at infinity and stretching down and into this T star S3. So then you can define an augmentation of the algebra. So here, if we're in T star S3, we have to put Q equals 1 because this S2 bound. So then what you do is you just mimic the definition of the differential. So you count holomorphic curves, now rigid ones, with positive puncture at the Rabe chord A, then stretching down inside LK and going back up if you follow the boundary. And the count of such curves gives you a map from the algebra into the complex numbers, or in fact into the first homology of the filling. And the fact that this is a chain map is exactly the same argument that d squared was equal 0. Because when you look at the boundary of one-dimensional moduli spaces, then you find the rigid curves inside their marked dimension 0 here, and then at infinity they fly away in this one parameter family. So this is exactly the composition epsilon composed D. And since it's a boundary of a one manifold, this is 0. Okay, so in particular, if we work in T star S3, then every knot or link has, well, let's say knot, has two natural fillings. So one is the Lagrangian conormal, and one is the complement of the knot. So you can get it by, say, Lagrange surgery on the conormal and zero section. And therefore, we find that e to the p is equal 1 and e to the x is equal 1, meaning just we fill in one of the cycles or the other one, belong to this augmentation variety for any knot. And in fact, for the unknot, this is equal to the augmentation variety, and it's the only knot with this property. But let me, I want to come to the end, so I won't discuss this more. There's much more to say. For example, maybe the most important thing is that a polynomial of a knot divides the augmentation polynomial. Okay, for q equals 1. Okay, but let's now try to go to, let's try to use LK inside of the resolved conifold in the same way that we did before for the exact L. Now, the point is that LK living inside X certainly does support holomorphic curves, holomorphic disks without positive puncture. And therefore, our argument will somehow fail. So we try to look at this one-dimensional moduli space with one positive puncture stretching down along LK, and we move it in there. But what can now happen is that we have this so-called boundary splitting. So there is a closed holomorphic curve splitting off along the boundary of this one-dimensional disk with positive asymptotic. So therefore, our configurations, which we want, the one on the previous page, or way back, do not sum to 0. So this is just part of the boundary of some manifold which has now a new kind of unknown boundary. However, this problem has been dealt with before in Floer theory by Fukaya Ota-Ono, and they developed a technique which is kind of called obstruction chains. And here what it amounts to is the following. So you take, this maybe not completely standard, this is a little bit, so normally obstruction chains deals with holomorphic disks that bound. But now they don't quite bound, but the same technique works. So what we do is we take for each holomorphic disk inside, we take its boundary, and that's now homologous to some multiple of the longitude. So we take a reference chain going from this disk up to infinity, where we just let the chain be standard multiple of the longitude curve. So now we can remove this unwanted boundary splitting by counting some other objects. Namely, here we see a picture of the boundary splitting forming, and then it forms. And instead of stopping, we now say that we go on and count holomorphic curves which intersect the bounding chain of sigma. So our count becomes much, much more complicated. Namely, we have to count not just disks, but disks with all possible insertions. But once we do that, then these somehow interior boundary is removed, and now the boundary is just again the vertical splitting. And so we see that our old formula that worked nicely in the exact case works also in the non-exact case, provided we count not just disks, but disks with insertions of these obstruction chains. Now, when you look at the splitting, of course, not all these insertions will happen in the inside of the manifold. Some of them will happen. At infinity. So it remains to explain what it means to count with insertions at infinity. This is, however, very simple, because at infinity all the curves looks like multiples of this x curve. So in order to see how often we can insert something, we just need to keep track of the how many times the curve at infinity wraps around the p. And if you think about it a little bit, that exactly corresponds to letting p be equal to the derivative of the Gromov-Witten disk potential. So if it wraps k times around, the derivative brings down a factor k, which should be multiplied by the factor of p we have in order to count these things. So this is in fact, this sort of corrected augmentation shows now that the Gromov-Witten disk potential, the derivative of it, locally parameterizes the augmentation variety. So now, the goal of the rest, I should maybe say that, let's see what comes here. Okay. So maybe I'll go back for a while and just comment on the fact that now, so for example, for this unknot, if you would like to determine the Gromov-Witten disk potential for this Lagrangian stretching down and filling lambda k, then what you have to do, well, you just have to solve for p in terms of x here and take the logarithm and integrate once. So it's a somehow very simple thing. And also for the second one, you can certainly do it. And I think if you compare to other methods for doing that, that is a somehow very simple way. So this counting things at infinity is somehow much easier. You get algebraic equations than counting things inside. Okay. Very good. So now I want to consider the somehow full quantization of this story. And what does it mean? It means that I would like to take the full genus story. So we just did disks, but I would like to somehow find all holomorphic curves of all genus on this Lagrangian LK. So it's somehow clear that you would have to look at curves of all genus at infinity in some sort of similar spirit. And that's actually not a very easy problem. So it corresponds to higher genus deformations of some Floer theory or something like that. But in this case, there seems to be a solution. And I will try to describe it in a while. But let me first somehow give you the structure of the theory and what we would get. So there are two main ingredients. So the first main ingredient is what's called the symplectic field theory potential. So that's a function. That's a generating function. It's a function which counts all possible rigid curves with boundary on LK. But now, just like for the augmentations, we cannot count just curves which have no punctures. Rather, we have to count all the ones which also have positive punctures. So in this case, for the knot, we had the dimension of a curve is just the sum of degrees of its of the Rabe chords at its positive punctures. So that means that we actually have here curves with no positive punctures, then those with 1 positive, 2 positive, and all of these positive have to have degree 0. So our counting function sort of schematically looks like a sum like that. So similarly, we would like to count, so at infinity we have this somehow stupid R translation, so we would like to count all the R families of curves up there with positive and negative punctures. And we call that the Hamiltonian and write it as H. And now, if we can avoid this interior splitting, so that we look at these one-dimensional moduli spaces of holomorphic curves with only positive punctures, stretching down along LK, so that all boundaries of this manifold are just corresponding to vertical splitting at Rabe chords, just like we did for the disks, then we would get some equation of the following form. So if we take, so e to the f, that means just take all disconnected curves of dimension 0 inside, then attach to it this h in all possible ways, at all possible Rabe chords and insertions or whatever it takes. And then we sort of leave some of these disconnected curves and we take them away by multiplying by e to the minus f. So this thing should be the boundary of a one-dimensional manifold, and therefore this equation should hold. And note that this is now very similar to the previous equation. So this is exactly somehow the higher genus counterpart of this augmentation equation. So in pictures, what I just said, so to get to somehow get a hold of this, what we're saying is that we have these blue one-dimensional curves at infinity and the red rigid curves inside, and when I stack them on top of each other with one blue and several reds, that exactly is the boundary of the moduli space of all the blue curves stretching down. Okay, and then we would have this equation. So one question remains to be addressed, and there's somehow what do we do? And that's the main thing. What do we do with these obstruction chains? But let's first note that we have to deal with at least the obstruction chains we did before for the disks or for other curves, right? So they have to have these bounding chains, it's called. So bounding chains going off to infinity. And again, we have to do all the possible insertions. Now, let's see what it means to count these insertions. So before, we had the picture to the left. So we had a disk stretching down, and we had two insertions of other curves. And to count that meant to count somehow the derivative of this potential squared. And then we had e to this thing, right? E to the p. So all these things. But now, when we have to deal with higher genus things, then we can also attach the same curve twice, and so on. So attaching the same curve twice means that we multiply by the second derivative of this potential. And then there are symmetry factors. So thinking a little bit more about that, we find that if you want to do this counting of all the insertions, then you should actually substitute the string coupling constant times ddx for the operator p. And then the insertions would count all the right things. So this is in some sense some kind of enumerative interpretation of high school quantization or something like this. So anyway, so now what we learn is that if we can cure this boundary splitting problem, then if we take h, let's see what comes next. No. So if we take this h and substitute inside h e to the p by e to the Planck constant ddx, then we should have this equation holds. Okay, and again, if you think about it, this e to the f0, the part of this counting function that just counts curves without positive punctures, that was actually by our correspondence equal to this HOMFLY function, HOMFLY wave function. And so if we are able to eliminate all the Rabe chords from the previous equation, e to the f, h acting on e to the f is 0, then we should get an equation of an operator equation for something that annihilates the wave function. So that should indeed be the operator equation corresponding to the recursion for the colored HOMFLY. Okay, so if we can construct this theory and compute it, we would have in some sort of sense a constructive way or to find this recursion relation, which is a little bit difficult task. So, let me give a kind of brief sketch of this construction or what it takes to construct this version of Legendrian SFT. So, the main point is that we need to have so before we had these rigid disks that interacted with a moving disk in some sense. So we could do with somehow stationary obstruction, stationary bounding cochains. But now this thing, as it moves, it can somehow intersect itself. And since we allow for higher genus, we have to deal with that as well. So we need to have some kind of dynamical obstruction chains. And the proposal here is to take a Morse function, which basically is a small perturbation of a Bott function, which has a minimum along a circle and then flows up to infinity. And now if we have a generic curve sitting inside there, then we take the obstruction chain, which is just a flow up along this from the boundary up to infinity, and we correct it by certain disks, which are the one fixed unstable manifold of the Bott minimum. So once we start doing this, we would need to calculate the intersections of these chains, and as I will show you, it's then inevitable to do this without more reference data. So we also need to have a forechain which bounds the Lagrangian itself with certain behavior at infinity, and starting out like the complex structure times this gradient. So let me just kind of tell you in pictures what's going on. So we need to check certain invariants, and this first piece is maybe the central one. So if you have two holomorphic curves, then basically what we're saying is that if their boundaries link, then we should count them with their linking number. So we need to check that as you cross through, the potential should not change. And that's a kind of gluing argument, and basically you're using this point many times, and so you regularize, and what you see is that the number of gluings is this magical e to the 1/2 GS minus e to the minus 1/2 GS. And it seems that this maybe one can use to prove something like Skane relation for HOMFLY purely in terms of holomorphic curves. But that's a different talk, so let's continue with this talk. So now the next thing where we see the need for this forechain is that in a one-parameter family, our boundary of the curve could become tangent to the gradient of f. And at that point, we can somehow borrow experience from real algebraic geometry or real algebraic knot theory, where in fact, when that happens, there is a new intersection between the interior of the curve and this reference forechain. So somehow, if you go from left to right, the count is unchanged, provided that you also count intersections with this reference forechain and the interior of your holomorphic disks. Okay. So, without kind of saying too much, this allows us to define a Gromov-Witten potential, which counts graphs with various linking informations at the edges and so on. So we get, in some sense, generalized holomorphic curves. I should point out, and I should have pointed out maybe earlier, that already for the Gromov-Witten disk potential, you would have to count trees where this linking, you cannot just count bounding cochain intersection with the main disk, but also in between the disks. So also the disk potential is somehow defined only if you pick obstruction chains. Right, so let me not somehow say too much more about that. The claim is that this outline works. There's a lot of mathematical work to make it really work and prove this, but it looks good. And let us look at a couple of examples where this is somehow successful. So for the unknot, there are no higher genus curves at all at infinity, and therefore this is the only example, I think, where you have to do no elimination theory. You have no chords at all. So this is just giving you the recursion relation where x and p are now operators. I should have put hat, but I didn't. For the Hopf link, there is again no higher genus curves except for formal higher genus curves. This is in fact a general feature. I'll tell you a little later. But there are input from disks with several positive punctures, which is somehow important. So before we had just, for the contact homology, we had just one positive and several negatives. Now we have a couple of positives and a couple of negatives making some sort of input. And okay, after some work, you can again solve this thing, and you get the following 3 generators for the recursion relation, which is in line with what you get for the HOMFLY. And note that it's not completely trivial check. So the first equation is pretty trivial, but the other 2 actually contain some genus business. And finally, there is the trefoil, where you can also do this calculation, and this is somehow, I don't have time to say anything about this, but it's actually rather non-trivial check with some, when you solve the equations, there is some kind of input from this linking change and so on. So it looks very good, and we get on the nose what you should. Okay, so in the final 1 minute, let me skip a lot of things, and let me just go to this last picture. So in the case when we have a knot, then the augmentation variety is an algebraic curve in C2. And so, and in fact it is somehow this curve that we saw in the previous talk. So if you can use it to build a mirror of the resolved conifold, and you can do some kind of B model calculation on that mirror. And for that B model calculation, you could try to do it by topological recursion. It's not completely clear that it works for torus knots, somehow check, but it's not completely clear. But I want to explain at least how you could actually compute the annulus kernel, which is the, for those who knows a lot about topological recursion, this is the key ingredient that we need. And so, as it turns out, one can linearize this homology at the given augmentation, and one can even prove by the fact that this Gromov-Witten potential is analytic function that for generic points in the augmentation variety, the homology is has rank 1 in degree 1. So now we can look at the annuli to the left in the upper row. So I'm drawing an annulus with a boundary on my LK and positive puncture at the Rabe chord, or actually it's the sum of Rabe chords that generate the linearized homology. And we can look at the splittings of this moduli space, and again, if we can do away with boundary splitting, so in particular if you have 2 not very close to each other, then it's really, you can do much of this without heavy use of this bounding cochain business. But anyway, so what we would find is the splittings on the right-hand side. But now note that if we pick this C to be generator of linearized homology, that means that D of it is 0. So that means that the count of these cylinders or strips, or augmented strips, if you want to be precise, that comes down is actually 0. So the first term does not contribute. And the second term is just the kind of closed disks hitting the bounding cochain of the annulus of the annuli that we are looking for. Okay? And similarly as this kind of homology check, one can check that the count of these curves when you take DDP is non-zero. That's at least stable. So we have something non-zero times the thing we're looking for is equal to this other split curve with kind of 2 outgoing legs, and then there's some sort of banana inside. Now the 2 outgoing legs, the upper part, we can compute from pictures, so just like we compute the contact homology differential. So what about the lower part? Well, in fact, the lower part can also be computed. And here we use the fact that the linearized homology in degree 0 is 0. So we pick a primitive of one of the positive ends A, and we look at the one-dimensional moduli space again on the left, and we have this equation, so the right-hand side is 0. Again, the curves at infinity we can see from pictures, and so we find that this red one is equal to the blue one at infinity divided by the strips where we take it to be 1. So then we have all the terms in this equation so we can solve for the annulus amplitude. Now, to finish, note that we can actually do the same thing for all genus. So if we assume that we know the red bit and everything with positive puncture for some kind of Euler characteristic down, down to a certain level, and we want to take next step, then we can just draw a more complicated picture in the inside, look at the splittings, and the only term that's not known is something non-zero times what we're looking for. So in some sense, recursively, we can determine the whole wave function, provided we know the holomorphic curves at infinity. And one can check that if you, at least if you fiddle a little bit with this Legendrian torus, then at the cost of introducing more Rabe chords, you can make sure that you have only somehow formal high genus curves at infinity. So basically, you have to find all these disks and then how they link, and then you write up all these holomorphic curves at infinity, and you should be able to do the recursion. Maybe there won't be ever a closed formula, but if you have a knot you really know and love, you can take a few steps in this recursion. So, okay, I'll stop at this. Thank you very much.